In this video, we'll talk about surface integrals of vector fields, which is also called the flux of a vector field over some surface, or across some surface. So imagine having a vector field in space, F. So it depends on x, y, and z, and has components p, q, and r, which themselves are functions of x, y, and z. Okay, and then we have a surface which is an orientable surface, which for us means that we have a clear definition of a normal vector across the surface that is continuously changing. So it makes sense to talk about a positive or negative orientation for our surface. So this surface is given to us by a vector function of two variables, just like before. So each component depends on u and v, and what the surface integral of this vector function across that surface of that vector field across that surface S is, so that's our definition. What it's going to be, it's denoted as follows. It's the surface integral of f across the surface S. So this is the notation, and from this dot product notation you can guess probably what's going to happen. We are going to look at the surface integral of a function which is obtained by taking the dot product of f on the surface, evaluated on the surface, with the normal vector at the same point on the surface. So what we are basically integrating is the normal component of our vector field across the surface. So what this is the surface integral of f on the surface with the normal vector at the same point at which the vector field is evaluated. So this is now a function of u and v, and that's what we are integrating over this surface. So of course we have to say what this normal vector is, and we can compute it once we have the vector function r, u and v. It is going to be the cross product of the partial derivatives of r, ru and rv, divided by its length. So it is a unit normal vector. Okay, so imagine we have a surface, for example the surface of a sphere, and then this normal vector at each point is a unit vector that is pointing and is perpendicular to the surface at every point. Okay, so this would be our positive orientation, but it's given, the point is that it's given by this formula, can be computed by this formula. This was our definition for the surface integral of a vector field. But we've seen that the surface integral of a function such as this is actually, so if I continue with these formulas and write n like so, I will get some simplification. So that is n, but remember the surface integral is actually just a double integral over the domain for the parameters u and v of the function that we want to integrate, times the length of the cross product of r sub u and r sub v. So that's exactly an extra factor that goes in there and cancels that factor which we have in the denominator, there I should take a dot product. So here we also have the dot product of f evaluated on the surface and the cross product of Ru and R sub u and R sub v. So this is the practical, well, the way we compute surface integrals of vector fields in practice. So let me give you an example and a question. So for example, let's consider the vector field f with components z, y, and x, and let's compute the surface integral of this vector field across the unit sphere. So our surface is the unit sphere. It is given by the equation x squared plus y squared plus z squared is equal to 1. So we can use these formulas to compute the flux of f across the unit sphere, or in other words, the surface integral of f across the unit sphere. So pause the video and use spherical coordinates to compute this surface integral below. Okay, I hope you paused it and realize that, okay, our vector function ruv is just, well, a function of, instead of uv, let me just reuse the spherical coordinates phi and theta. So r phi and theta is just the sine of theta, cosine of phi, cosine of theta I, sine of phi, cosine of theta j, and the cosine of phi k. If you use this vector function where, of course, phi changes from 0 to pi and theta changes from 0 to 2 pi, and compute this cross product, so compute the derivatives of r with respect to phi and theta, and then of those vectors you compute the dot product, you will get the following vector. It's going to be the sine squared of phi times the cosine of theta I plus the sine squared of phi times the sine of theta j, and finally we have plus the sine of phi times the cosine of phi k. So this is going to be the cross product with which we want to take the dot product of f when we evaluate it on the surface. So we look at what values, what vectors f has on the surface of the sphere. So f r phi theta is the cosine of phi I, because the first component is z, and z for our sphere is the cosine of phi. Then we have plus y times j. Y is the sine of phi, sine of theta. So that's the j component. And the third component is x, which for our unit sphere is sine of phi, the cosine of theta, cosine of theta, k. Okay, so what we have to do is take the dot product of these two vectors and then integrate that over the domain where phi changes between 0 and pi and theta changes between 0 and 2 pi. Okay, so the function that we end up integrating is going to be 2 sine squared phi times the cosine of phi times the cosine of theta plus, so that's from various components like this one and this one. There you have the two things, these expression twice. Then we have the sine of phi cubed times the cosine of phi times the cosine of theta. No, sorry, that's the sine. It's the sine of theta squared is what we have there, sine of theta squared. So this is the function which we have to integrate with respect to theta and phi. So that integration is not too complicated. We've seen similar integrals before. So when you do the integral, let me continue over here, you will find that in the end you will have an integral of sine cubed of phi with respect to phi as it changes from 0 to pi times the sine squared of theta with respect to theta as it changes from 0 to 2 pi. And these ones you can evaluate and find the value to be 4 pi over 3. Okay, more details can be found below. Okay, I hope you enjoyed this video and I'll see you in the next one.